Good morning friends, welcome back. Today we'll see two important theories in the unit 2 of CH1501 friends, right. These theories are about empirical formula and more molecular formula calculations friends, right. So first of all, what is empirical formula friend? Empirical formula is the simplest formula expressing percentage composition of different elements present in a substance, which is known as empirical formula, or it is also known as simplest formula. For example, benzene friend, C6H6. If I divide by 6, what I will be getting? CH. So for benzene, the simplest or empirical formula is CH friends. One more example. It gives the simple ratio and not actual number. I am talking about empirical formula, right. It gives a simple ratio and not actual number of atoms present. For example, you know that you have used this formula for glucose. If I ask what will be the empirical formula of C6H12O6, so it becomes CH2O, because when you divide whole with the 6, so 6 divided by 6 it becomes 1, 12 divided by 6 it becomes 2, and oxygen 6 divided by 6, that is again 1. So CH2O will be the empirical or simplest formula for the given molecular formula of glucose, for example C6H12O6. So what is our target? Target is to get the empirical formula of the numerical given, and then we will go for one more step further towards the molecular formula. But how to get empirical formula, friends? So to derive the empirical formula, spelling mistake, there are following steps, friend, that we have to follow. Number 1, right, you will be given the percentage of different elements. So in the first step, you have to find out relative number. How to find relative number? It is simple. As I mentioned, percentage of each element or atom will be given to you. You divide this percentage of the given atom by its atomic weight, friend. And for that you remember the atomic weight of some of the common element. And I know that you remember, you have that idea, carbon 12 for example, oxygen 16 and all that one, friend, isn't it? So this is the first step. What is the first step, friend? Get the relative number. Percentages are given in the numerical. You divide with the atomic weight of the respective percentage of the atom given to you. You will be getting relative number. You will be getting some the values in the form of relative number of the elements given or atoms given. Second step, find the ratio of quotients by dividing each one by the smallest quotient to get the simple ratio. That means in the second step your target is to get the simple ratio of the atoms or elements given in the numerical. In the first step you got relative number. Out of relative numbers, 3 or 4 relative number of different atoms that you got, find out which one is the smallest one, right, and then all the other atoms you find that relative number is higher side, you select the smallest one and divide the relative number of all the element with the smallest one in the step number 1, which is going to give me simple ratio. So the step number 2 is find the ratios of quotients by dividing each one by the smallest quotient to get the simple ratio, right. From the step number 1, relative number are used, right, dividing all the relative number with the smallest relative number to get that ratio, which is known as simple ratio. The third step, in the third step, if the simple ratios, that is output of step number 2, are fractional, most of the time it will be fractional, reduce them to the simplest possible whole number by multiplying throughout by a suitable integer to get simple whole number, friend. It is nothing but, friend, if you are getting, suppose you are getting 79.88%, what you will say to your friends and family? 79.88, I got 80%. Simple, isn't it? So this is the same thing. Simple ratios are fractional. You are going to convert it into the simple whole number which is the nearest, isn't it? We'll see that one in the all these steps I will talk to you in the next slide, where I have taken example, right? So that will clarify all this step 1, 2, 3 and 4. But what is 4? Look at this simple 4. Write symbol of the elements and above whole number that you got here, right? This whole number as a subscript to get empirical or simplest formula. For example, you got the simple whole number for carbon is 1, hydrogen is 2 and oxygen is 1. Then you will write the elements carbon, hydrogen and oxygen. What is the simple whole number for carbon is 1? So if you write it on, it is understood that it is C1. Hydrogen it is 2, oxygen is 1. This is how you will be able to write the simple or empirical formula. What are the 4 steps? First is to get the relative number, second one is to get the simple ratio, third one is to get the simplest whole number, and the fourth one is to write the empirical formula. Friends, in the next slide I am going to take all this thing into actual practice, so it will be much more clear to you. But in that you have one more additional step. Let me say step number 0, right? What is that? That we will see, and then we will follow 1, 2, 3, 4. Or if I have written there 1, 2, 3, 4 like that, then the 0 it will be step 1, then this step 1 will be step 2 like that. But it will be easy for you to understand, don't worry friend. Numerical. Okay, so this is the numerical. All the previous 4 steps of the previous slide I am going to perform, so it will be clear to you. In an organic compound, one analysis is there which says that this particular sample contains 65% carbon, 3.5% hydrogen and 9.5% of nitrogen. Derive its empirical formula. So what is the first step? So called 0 step, friend. So here if you add this percentage of carbon, hydrogen and nitrogen, 65 plus 3.5 plus 9.5, it is not coming out to be 100%, friend. It is less than 100%. So there is a thumb rule. What is that thumb rule? If the percentage of different atoms or element given is not equal to 100%, right, summation of this atom or elements percentage is not equal to 100%, remaining percentage will be percentage of oxygen. This is unsaid in the numerical, but this is a thumb rule. So here as we are getting summation of 6 plus 65 plus 3.5 plus 9.5 not equal to 100, the remaining percentage, it should be 100, but if it is not, don't worry, because remaining is the percentage of oxygen. So 100 minus the summation, right, which is coming out something around 79.1. So 100 minus this value will give me 21.91, which is nothing but percentage of oxygen. Friend, it was not given. So this is what I said, first step, or you can say 0 step. First you have to see whether 100 is there, not there. You have to put this thumb rule into action. So actually your sample in this numerical contains carbon 65%, hydrogen 3.5%, nitrogen 9.5%, and it was not given, but we calculated oxygen as 21.91%. Clear, friend? And you know, some of them you have the mathematics background, percentage are always based on 100, isn't it? Done. Now the previous slide, it was step number 1, but here it is 2. Don't worry, because we are going to calculate relative number. And what was the method? Again I will repeat, friend. I said in the previous slide that if you want to get the relative number, what you have to do is find the percentage of that relative atom or element and divide by its atomic mass. So here in this numerical 65% of carbon is there, divide by its atomic mass of carbon, that is 12. So I am getting relative number, friend, right? So dividing percentage of the atoms or elements by its atomic weight, right, respective atoms or elements atomic weight, what we are going to get is the relative number. So relative number of carbon is 5.41, of hydrogen, the percentage here is 3.5, divided by its atomic mass 1, 3.5 is the relative number of hydrogen. Nitrogen 9.5 is the percentage, atomic mass is 14, friend, listen to me. If it is physical class, I would have confused. Right, first I will ask, what is 7 for nitrogen and what is 14 for nitrogen? Friends, don't use the atomic number, atomic mass you have to use. Don't get confused, right? So 9.5 is the percentage of nitrogen in this numerical divided by atomic mass of nitrogen element, that is 14, gives me 0.685. Smallest one, I am going to use this one in the next step, that is why I have circled it. Oxygen, you calculated percentage is 21.91, divide by its atomic mass 16, you are getting 1.36. So out of 4 relative numbers, right, here the smallest is this particular. Go for simple ratio. Dividing each relative number with the smallest relative number, we get the simple ratio, right? And then we will convert into simple whole number. So simple ratio, how to get? See, 5.41, this is 5.41, divide by 0.685, smallest in the previous step. 3.5 is this particular value, relative number of hydrogen, divided by the smallest. 0.681 divided by 0.681, that means at least one simple ratio will be 1, because out of the possible values of the relative number, 1 is going to divide by itself. So this is going to be 1, right? The next one is the simple ratio for oxygen, relative number found in the first step, 1.36 divided by 0.685, it is giving me 2. So see, these are the simple ratios. As I said, you convert into the nearest integer to get simple whole ratio. So 7.898 is almost 8, friend, right? 5.11, lower side, lower integer is 5 here, 1 is very nice, it is also 2, no problem. See friend, when you calculate at your place, you will get little plus minus than what I have calculated, but when you convert into the simplest whole number, it will be 8 for carbon, 5 for hydrogen, 1 for nitrogen and 2 for oxygen. And therefore I am writing the empirical formula after writing the symbol carbon C, hydrogen H, nitrogen N, oxygen O, this number as subscript. Carbon 8, hydrogen 5, nitrogen 1 and oxygen 2 is the empirical formula of this particular compound. Clear friend? But I am not going to stop here. This is empirical formula calculation. I want to talk to you about molecular formula. So how to calculate from empirical formula knowledge reaching up to the higher step, that is molecular formula. One more numerical friend. Okay, see, this is the numerical 2 or 3 step numerical friend, right? 2 or 3 different laboratories they have given the analysis report, and based on this analysis report we will find the molecular formula, friend. Okay, an organic monobasic acid analyzed by 3 different labs, for example, friend. This is lab 1. Report says that this monobasic acid, right, which you have taken for calculation of molecular weight, this sample, the laboratory 1 or student group number 1 says that, sir, we took 0.193 gram of this acid, right? After our experiment, it shows that 0.1320 gram of the carbon dioxide and 0.027 grams of water vapor. After complete analysis, laboratory 1 has given the final concluding remark. What is that? As A, 0.1935 gram of this acid gives us, after analysis, what you can say, 0.1320 gram of carbon dioxide and 0.0270 gram of water. Laboratory 1. The laboratory 2 says, sir, we will give you direct one line conclusion. What is that? It says that, laboratory 2 says that there is a presence of 55.04% of chlorine. Very nice, ready to use data. Okay. The third laboratory most, what you can say, time consuming result. What they say is that, or third group of the student, they say that, sir, when we took 0.2709 gram of this acid, monobasic acid, analyzed in our laboratory, right, after dissolving it in water, right, and then if we try to neutralize from the burette, I am adding, because this is acid, and how much acid I have taken by the lab 3, 0.270 gram dissolved into the minimum or required amount of water from the burette for neutralization, acid base titration. Lab 3 says that 25.20 ml N by 12 NaOH was required. Now your job, calculate empirical and molecular formula of this acid, monobasic acid. You have to find molecular formula, friends, right? But for that, first of all, you have to have understanding about the empirical formula. You know now empirical formula. What do you mean by empirical formula? How to calculate it? But for calculation of the first relative number, you required percentage, friend. All percentages are not given here. Therefore, lab 1, the report of lab 1, we will find the percentage of carbon, percentage of hydrogen, right, etc. So how to find? Because lab 1, some indication is given in the form of carbon dioxide, so I will be able to use this value, this report, for percentage of carbon. Some indication is given by production of water by the experiment done by the lab 1 and its report. I will use and convert it into percentage of hydrogen. Okay, fine. Let us do that exercise first. Calculation of percentage composition of the elements based on lab 1. Based on lab 1, friends. Right. Okay, be with me, friends. Now, see, when carbon dioxide, right, having the molecular weight 44, it is molecular weight. 2 oxygen, 36 plus 1 carbon, 12, 44. There is 1 carbon only, isn't it? And what is the atomic mass of that carbon? 12. So if you are given 4 grams of carbon dioxide, you can easily say that I have 12 gram of the carbon. What we are doing? Calculation of percentage of carbon, friend. So 44 carbon dioxide will correspond to 12 gram of carbon. Here the carbon dioxide produced by lab 1, right, from the weight 0.1320 gram, this is the carbon dioxide weight. Can I find out the amount of carbon? Yes, simple. 0.1320 gram multiplied by 12 divided by 44. So when you try to solve, you are going to get the amount of carbon. Let me say it is y gram. You have the calculator, you can calculate. Now I want percentage of carbon. Relative number is always based on percentage of carbon. How can I convert this amount of carbon in percentage? Simple. See, friend, what was the sample taken by lab A? It was here. See, the amount of sample taken 0.1935. If 0.1935 gram of the substance corresponds to y gram of the carbon, for 100, what will be the carbon? That will be the percentage of carbon, friend. So this 100 will be multiplied by y. See, 100 into y divided by this 0.1935 divided by 0.1935. But what is the value of y? It is already there, friend, with us. So y, I will transfer this value here in this equation. So 0.1320 gram into 12 divided by 44 multiplied by 100. So it is 100 divided by the weight of the sample 0.1935. So this is nothing but your value of y. And if you solve this, it gives me 18.6%. This is nothing but percentage of carbon, friend. Right? So laboratory A, first part, it gives me the percentage of carbon, friend. The second one is the same sample 0.1935. You are getting the analysis done. Water produced is 0.270 gram. So can I use it for percentage of hydrogen? Yes, simple. This is the same method that we have used for percentage of carbon. Let us do it in the next slide. See, 18 grams is the molecular weight of water, isn't it? There are 2 hydrogen. So, in that case the weight of hydrogen will be 2 grams, but water produced in the result of laboratory A, as we have seen in the previous slide, is 0.0270 gram. Then what will be the amount of hydrogen in that water? So, this will be directly multiplied by 2 divided by 18. So, 0.270 multiplied by 2 divided by 18. So, let me say this is the x gram. What is this? This is the x gram is the, what you can say, weight or amount of hydrogen here, friend. I want to convert it into what? Percentage. Therefore, suppose 0.1935 gram substance gives me x gram of the hydrogen. Percentage is always based on 100. Therefore, 100 gram will corresponds to what? So, 100 multiplied by x divided by this weight, that is 0.1935. Substitute these values from x. This is the x you are going to get, and it is going to be multiplied by with what? 100. So, the x is 0.0270 multiplied by 2, right, divided by 18. So, this part is your x, friends. Okay. And then what you to do, you multiplied by 100, this is 100 divided by the weight of sample 0.1935, and if you solve, this gives me 1.55 percentage of hydrogen. Thank you, lab 1. Based on your report, I was able to calculate percentage of carbon and percentage of hydrogen, friend. Lab 2, you are very smart. You are giving me directly the percentage of chlorine, isn't it? It is given in the numerical 55.04, friend. Now, if thumb rule, if I add all this percentage of carbon, which we have calculated in previous slide 18.6, here we calculated percentage of hydrogen 1.55, and percentage of chlorine is given 55.04. Is it coming out to be 100? No. Then what is thumb rule? Remaining has to be percentage of oxygen, right, friends? So, this summation comes out to be something around 76%. Therefore, remaining 100 minus this summation gives me percentage of oxygen, friend, 24.81. Now, you have the 4 elements in this one: carbon 18.6%, hydrogen 1.55%, chlorine it is already given 55.04%, oxygen just we calculated based on the thumb rule 24.81%. Let us move for the empirical formula. Now you know, yes, you can go for relative number. I made it very easy for you because you have to go for second journey also, that is molecular formula. Elements: carbon percentage 18.6, hydrogen 1.55, chlorine 55.04, oxygen 24. What is the atomic mass of carbon? 12, hydrogen 1, chlorine 35.5, oxygen 16. So, if I divide this 18.6 by 12, relative number, it is coming out to be 1.55. 1.55 is the percentage of hydrogen divided by the atomic mass of hydrogen. This gives me 1.55. 55.04 divided by 35.5, again I am getting relative number 1.55. 24.81 divided by 16, it is going to give me 1.55. Sir, you have adjusted all this value, all of this we are getting 1. No, friend, it is real example. When I will show you the compound, right, then you will say that yes, this is the actual compound, friend. So, we have to find out the simple ratio. So, what is the simple ratio? Smallest one you have to find out of these 4, and all the relative number you have to divide by the smallest one. But here it is no question, all of them they are 1.55. So, all of them will be divided by the smallest or equal, that is 1.55, getting carbon simple ratio 1, hydrogen 1, chlorine 1, oxygen 1. So, you are getting simple whole number, right, 1, 1, 1. So, how to write empirical formula? Write the symbol and this simple whole number as the subscript. So, the empirical formula of the given monobasic acid is CHClO, friend. So, first part is over, friend, right. Now, the most important part. Before we go for the most important part, that is part number 2, Let me talk to you little bit about the theory part first. The relation between empirical formula and molecular formula in the next slide, friend. Okay, here you will find one equation that we will use later also. Molecular formula gives the actual number of atoms present in the molecule of a compound or substance. Sometimes empirical formula and molecular formula can be the same. Therefore, I can say molecular formula can be same as the empirical formula or simple multiple of it. That means empirical formula you multiply it by some common value and you will be getting molecular formula. For example, CH is the empirical formula of say benzene. If I multiply both carbon and hydrogen by simple value, that is 6, you are going to get C6H6. That is your molecular formula. Therefore, the molecular formula you can say that is equal to empirical formula n times. Or you can say, if you want to find out what is that n, you can say that n will be equal to molecular formula mass divided by empirical formula mass. Friends, purposefully I kept it this red orange. I will use this equation later. Do you remember what is this equation stands for? Very nice. Have you got idea what is the difference between molecular formula and empirical formula? I hope yes. Fine. Let us we move for the second part. After little bit understanding of the theory, this is laboratory 3. What lab 3 says that 0.2709 gram of the acid, when it is dissolved in water, the solution was neutralized by NaOH from the burette. For that, the NaOH consumed was 25.20 ml. Normality of that NaOH was n by 12, that is 1 upon 12. Right. Therefore, this result or report of lab 3 we are going to use for what you can say the value n, etc. How to do that one? Be with me, friends. The most important part. See, friends, I can assume that you know the understanding of equivalent weight, normality, molecular weight and all that one. In that connection, listen to me. 25.20 ml n by 12 NaOH, if it neutralized this much grams of given monobasic acid, that is 0.2709 gram of the given acid. Assume that I am using 1000 ml, that is 1 liter, 1 normal NaOH, then what will be the amount of my acid on the right hand side? Can I calculate on the basis of this one? Simple, yes. Right. So 25.2 n by 12 NaOH correspond to this much amount of the given acid. What if it consumes 1 liter 1 normal NaOH? If I can get this amount, friend, it is nothing but your equivalent weight. This is theory part. Therefore, simple calculation, 1000 into 1 normal, directly it is going to multiply it by this value, mathematics. And this part 25.2 and n by 12 goes into the denominator. So 1000 into 1 multiplied by 0.270 and 25.20 divided by n by 12. N by 12 is nothing but if you have calculator you can directly write 1 upon 12 value here. Simple, friend. When you solve this, right, as it is 1 liter 1 normal NaOH, it is going to give me equivalent weight. Right. So 25.2 n by 12 NaOH corresponds to 0.270 gram of the given acid. Then 1000 ml 1 normal is going to give me the amount, which is nothing but equivalent weight based on theory part. So if you solve this, you are going to get the equivalent weight, friends. 129 grams. Friend, in the first line I said it is monobasic acid, isn't it? Therefore, use this information here. Molecular weight of any acid will be equal to its equivalent weight divided by multiplied by basicity. We have seen this in silver salt method. So equivalent weight just now coming out to be 129 molecular weight is equal to equivalent weight into basicity. Basicity is monobasic, therefore 1. So 129 multiplied by 1, it is its molecular weight, friend. Both are equal, isn't it? Equivalent weight and molecular weight, 129 grams per mole. Now let us go for molecular formula. Friends, for molecular formula you have to remember this equation number 1. What it says, that molecular formula, right, shows the actual number of the atoms present in the molecule of a compound. It can be same as the empirical formula or simple multiple of it. Simple multiple of it, how to calculate that one? Simple. N, molecular formula mass, friends, divided by empirical formula mass, right. So let us we see the molecular formula mass and empirical formula mass is with us. So is it possible to calculate or find N? Yes, we'll go for in the next step, friends. Okay, from the previous discussion, friend, what we have obtained is the empirical formula. It was CHClO, right, first part. Therefore its formula mass will be 1 carbon, 1 hydrogen, 1 chlorine, 1 oxygen, 12 hydrogen, 1 atomic mass. I am using 35.5 for chlorine and 16 for oxygen atomic mass. So this empirical formula is having empirical formula mass, summation of all these 4, 64.5, friends. Friend, I told you I am going to use this red equation 1. So this is the equation. N is equal to molecular formula mass, just you have calculated last part of the previous slide, empirical equivalent weight multiplied by basicity, 129 multiplied by 1, this was your answer. So equivalent weight was 129 multiplied by 1, monobasic 129, this was the molecular weight, that is molecular formula mass. Empirical formula mass of the same acid, just you calculated 64.5. If you divide 129 by 64.5, what you are getting as N? 2. Therefore what is molecular formula? N time empirical formula. Therefore the molecular formula is empirical formula taken 2 times. So empirical formula CHClO twice. So if I open this bracket, carbon 2, hydrogen 2, chlorine 2, oxygen 2, friend. Actually your job is over here, friend. This is the molecular formula. But one step further. As the compound is monobasic acid, friend. Monobasic acid, that means there is one COH group because no other elements are there. Otherwise acid can be sulfonic acid group is there, possibility in organic, but here it is not the case because carbon, hydrogen, chlorine and oxygen, only these are the 4 elements and it is monobasic, therefore COH group is there. Now what is the molecular formula? C2H2Cl2O. Now I will subtract COH. So 2 carbons were there, 1 carbon is minus, so only 1 carbon is left. 2 hydrogens were there in the molecular formula, I will minus 1, so I am left with 1 hydrogen. 2 chlorines were there, both the chlorine is going to remain as it is after subtraction. Molecular formula minus COH. 2 oxygens were subtracted, so no oxygen is left, so I am left with CHCl2. So first part of this structure is COH because it is monobasic acid. If I subtract it from its molecular formula, you are left with CHCl2. If I write separately, friend, CHCl2 is what? 1 chlorine here, 1 chlorine is here, hydrogen is here. So 2 part, friend. One is COH part, second one is, if I combine these 2, right, combining COH and CHCl2, I am going to get this particular compound after combination of these 2 fragments. And what is this? Dichloroacetic acid, friend. It is a monobasic acid, friend. So see, your molecular formula is also fitting into this one, right? Its empirical formula is also fitting into this one, friend. So this is how, based on 3 laboratory results A, B and C, using empirical formula, definition of molecular formula, empirical formula, theory part, we are in a position to get not only molecular formula but some additional part, right, I have used here to get the structure of this compound also. So this is dichloroacetic acid. Thank you, friends.